Stanford University.
All right, good morning. So basically, today, the key word going to be is coherent, right? So that's what mostly I'm going to try to tell you about with it, because that's sort of my background. And while people are coming in, I'll mention, first of all, it's difficult to follow. The previous lecture was a Nobel Prize winner, right? So I have to, kind of keep up to that. One thing I wanted to mention is that I was actually here, I believe this was first. Was this the first one? The first Ultrafast X-ray Summer School in 2007. I was a postdoc then, but I was actually a participant there 7 years ago. I think iPhone just came out, so all the students were talking about that. So that should give you a sort of a time scale for things, and that was a lot of fun, and that's what I actually started learning about ultrafast X-ray science. And one sort of more philosophical note, I was trying to look up who this quote belongs to. It's difficult to make prediction, especially about the future. Some people say it's Niels Bohr, some people say Yoga Bear. I'm sure if you Google enough, you find it's Mark Twain. Mark Twain said everything. What I wanted to say basically here is that we probably still, I would argue that we still probably don't know what's the best use for XFELs is. We know that some experiments are perhaps more successful than others, but it's still a very new type of machine. And perhaps it's up to you guys to figure out what is it going to be useful for. One example that I wanted to use is that in my field, coherent X-ray science is now quite commonplace at most of the third-generation synchrotrons. Some of the techniques I'll show you today are based on sort of observation of this X-ray speckles. But if you look at the scientific case for justification for the third-generation synchrotrons, it was not even mentioned there. So all the things that I'm doing now, or a lot of other scientists do now at third-generation synchrotrons, was not anticipated until the sources were built. And so you can flip it around and ask yourself, what are we missing now? What are the crucial experiments or the crucial type of measurements that we could do at XFELs? I assume most of this school is about XFELs that we're not thinking about now. So I want you guys to think a little bit outside of the box. I'll show you what is possible, but try to think, for yourself. And I think it requires new people coming in from completely fresh background to really start innovating in that direction, in new directions, right? A lot of us started doing synchrotron work and then sort of expanded into XFELs, but I think you need some complete, blank slate minds to really approach. XFELs are very different types of machine. That's what I'm trying to say. OK, so this is my talk primarily is going to be, you can see all these beautiful pictures if you go around guest house or if you go on the SLAC website. And all of them basically show the X-ray speckle, or the fringes that have to do with the spatial coherence of the source. And my talk today is going to be to try to convince you that this X-ray speckle could be very useful. The XFELs are basically, they have two main differences from the traditional sources, not only that the pulses are ultra fast, but also that this is essentially almost fully spatially transversely coherent source. And the fact that it's ultra fast has been essentially used in almost every experiment, but the fact that it's spatially coherent has not been used in as many experiments as I think it should be. And so I'd like you to start thinking about what is possible. What can we use the speckle for? Why should we care about the fact that it's spatially coherent? So why do we want to do ultra-fast measurement? This is sort of my take. A lot of times you want to freeze time, right? So if you want to take a snapshot of some process that is very fast, like chemical reaction, or if you want to do, let's say, probe and destroy type of measurements on single molecule imaging, you need to have a camera that can basically, you need to be able to take a snapshot faster than the process happens. Otherwise, you smear everything out. Everybody who's doing photography knows that if you have a child running around, you have a long, slow shutter, you'll get a blurry image. But you can sort of argue that we can approach this question from the point of view of technology and ask yourself, how quickly can we do something, like switch a nanomagnet, or have a light switch or something like that. Or you can ask yourself, as a physicist, a condensed matter physicist, you can ask, how quickly can you drive a phase transition? So from chemical, biological, or physical, or maybe even technological point of view, you have very different types of questions that we ask. Another sort of angle is that we can induce non-equilibrium type states that create phases that may not be possible at equilibrium, where you allow everything to equilibrate. So that's, I think, is an interesting angle. And another angle that's sort of related to that is that a lot of times, especially in condensed matter physics, you have complex coupling or interplay between many degrees of freedom. In order to unravel them and figure out who's the driver, who's the passenger, you can do this by using ultrafast excitations. The response time for lattice, spin, and charge degrees of freedom could be very different. Typically, we think of lattice as slow, charge as fast, even though we find more and more examples. We discussed it a little bit this morning even, that actually that sometimes it's not the case. But that could be another sort of tool in order to study systems that are that have these couplings. Okay, so kind of going back, so this is the picture. Probably you've already seen this somewhere or somehow, and maybe even in this slide. The idea is basically to go to this ultrafast regime and find out what is the technology, what is the materials properties, what are the phase transitions, how can we control phase transitions in this very fast time scales and at very small length scales. This is why X-rays are good at seeing things that are below this length scale of below this essentially wavelength of visible light, and then ultrafast word here describes what happens at these ultrafast time scales. Let's say picosecond and below. And so this is sort of to illustrate again my point that as a condensed matter physicist, I like to think of most of the hard condensed matter physics has some sort of complex interplay of these degrees of freedom: charge, spin, lattice. Sometimes people add orbital in there. And again, going to ultrafast regime can allow us to actually figure out what are the errors connecting these different degrees of freedom are. And why is this important? Well, because many of the condensed matter phases, they basically arise from that competition between a frustration between many degrees of freedom, and that creates superconductivity, magnetism, insulating metallic transitions, and so forth. So basically, almost every electronic or magnetic phase that you can imagine results as a due to the competition between charge, orbital, spin, and lattice degrees of freedom. Very often, fierce competition that results in frustration, for example. As a result of that, you also have some spatially inhomogeneous distribution. In other words, these phases that I'm talking about are very often very patchy, and they have nanoscale, what is known as nanoscale phase separation. That is, if you think about high TC superconductors or manganites or a metal insulator transition in simple oxides, very often they're characterized by this texture, nanoscale texture. And that's going to be important too. So not only we want to look maybe at temporal response of some of the systems, but also we have to keep in mind that a lot of them have spatial inhomogeneity, and that's where coherence could play a key role in trying to understand what happens here. And I'll come back to that slide a little bit later. Okay, so this is the slide I like to show. If you think about how fast the CPUs has grown over the lifetime, over basically, people's lifetime over 60 years, they've grown by about 12 orders of magnitude. So everything that we have at our disposals, our iPhones actually have more computing power than supercomputers 15 years ago, and that's all a result of this what is known as Moore's law, the fact that you have doubling of CPU speed every couple of years. But if you look at the similar growth in terms of the brightness of X-ray sources, we're going even faster. We're going about 18 orders of magnitude in just one person's lifetime. And that's, I think, is quite a remarkable achievement. It also explains why I think a lot of us are struggling to analyze our data, because the computers don't keep up with the amount of data that we can generate in sources like LCLS. Another type of, and so a lot of times people like to compare, in fact, in this slide, you see LCLS and APS sort of, which is this traditional storage ring that a lot of us older people have, still using, I guess, third generation synchrotrons. And a lot of times people say, what is the difference? What is the comparison? And I would argue that this is a terrible thing to do, to try to compare the two. They're very different animals, right? It's like comparing sharks to elephants or something like that. They've never met. They don't know about each other. There's nothing similar about them. There's very little overlap between the two, I would argue. But let's do this anyway. So let's basically, what I would like to do is, this is more traditional synchrotron storage ring, like Advanced Photon source near Chicago. Some of you may know or may have been there. And there are other sources like that. And then this is LCLS, where right next door. So if you compare the one slide that, of course, people from Stanford like to show is this one. This shows peak spectral brightness, and we'll talk about what this means in 1 second, instead of the average brightness. And in peak spectral brightness, the jump between, let's say, this APS, ESRF type storage rings is about 10 orders of magnitude. If you look at these numbers, it goes from 23 here to 33 or something like that. That's a huge jump. And there is only a 100-time increase in terms of the actual spectral brightness. In fact, if you look at the average number of photons coming out every second, if you're sitting at the beamline at a storage ring, let's say APS, or if you're sitting at the beamline here at LCLS, number of photons coming out on your detector per second, averaged over a long time, is going to be roughly the same, give or take an order of magnitude. And so it's interesting that, first of all, even though the number of photons, the flux, is about the same, the spectral brightness here of SLAC is about 100 times better. And that has to do with the fact that it's fully spatially coherent, whereas APS is not. And that is taken into account here in the brightness calculation. But if you divide it as the peak value, it goes up by, it's about 10 orders of magnitude higher. So what does this 10 orders of magnitude higher fact come about? Why is it so different? Well, it's because it's a very different type of source. So first of all, think about what else has changed by a factor of 10 to the 10 in 10 years, right? This is basically, this slide shows you that, in 10 years, we went by about 10 orders of magnitude in terms of if you're interested in peak spectral brightness. And we'll talk about what it means in a second. It increased by 10 to the 10. I couldn't come up with anything else that has changed, that much in technology or, at any given time, I think, in human history. I couldn't think of any. Maybe some of you, does anybody know what has changed by 10 to the 10th in 10 years in human history? I don't know if it's maybe the amount of data we'll all generate on YouTube or something like that, but I even doubt that. But basically, the reason is the following, that the storage rings typically operate, they're very rapid machines. They operate about 10 megahertz, let's say, ranges up to 100 megahertz for some machines. Let's take 10 megahertz as sort of the benchmark, whereas XFELs is 100 megahertz. So you have the same, remember, we have the same number of photons coming out per second, but storage rings has about 10 to the 5 more pulses. That means that each pulse packs 10 to the 5 more photons at LCLS as compared to, let's say, APS. So that's a big number already. And then pulse duration, again, if you think about typical storage ring, about 100 picoseconds. At XFEL, it's about 100 femtoseconds. It's about 1,000 times shorter pulse. That means that if you're interested in the peak value, you're going to divide by another factor of 10 to the 3. So it means that you squeeze all your photons. Not only you have 10 to the 5 more photons per pulse, you also squeeze your photons in 1,000 times shorter duration. And that already helps you to understand how different XFELs are compared to the storage rings. That's only 10 to the 8. So what is another factor of 100? This missing factor of 100 basically comes from the fact that LCLS and other sources like that are essentially fully spatially coherent. That means that they're diffraction-limited sources. You can also think about it if you've taken the E&M class recently. It's a plane wave, whereas at sources like APS, the wave is more chaotic. And if you look at the wavefront, it's sort of all warped and curved in places. So to select a single flat section of the wavefront at storage ring, you have to throw away about a factor of 100 or 1,000. In some cases, it depends a little bit on energy and other parameters to get to the essentially fully spatially coherent source. OK, so this is another slide. I'll flash this very quickly. I make this number kind of almost the same, even though there's a little bit of fudging going on here. But you can think about total number of X-rays per second at LCLS or APS is about the same. But number of pulses is different, and number of X-rays per pulse is also very different. You can also think about traditional storage rings as basically almost quasi-CW. CW stands for continuous wave, where you have about nanojoule per pulse, but you have nanoseconds between the pulses. So you have many, and the duration is picoseconds. So you have almost if you zoom out and squint your eyes a little bit, you can almost argue that this is a flat, continuous source of photons that come out as soon as you open the shutter. They come out like water out of the faucet, basically all the time. Whereas at LCLS, you have millijoule instead of nanojoule, and millijoules in some cases even more, and you have milliseconds from one pulse to the next, and each pulse is about femtoseconds instead of picoseconds. That helps you to understand that I think these are two very different types of sources, and it's almost impossible to even come up with an experiment that is you want to do at one machine, but you could also do it at another machine. Basically, there's very two different types of science, I would argue, that the two sources can access. So what is this brilliance that we were talking about? So let me give you a bit of a primer. I'm not sure exactly. Maybe some of you already know about this, and maybe somebody already talked to you about this. But the main idea is that what is interesting about when you talk about the property of the source, we define something as known as emittance. And emittance basically is the size of the source times the divergence, the angular divergence. And that product is called emittance, and that product is basically more or less conserved if you use normal optics. That means that you can increase divergence. For example, if you focus the beam to smaller spot size, you also have to increase the divergence so that the product stays the same. And so that's a very useful thing to know, because once you define this emittance, this product of divergence and the size of the beam, any optical manipulation of the beam does not affect that product. If you want to make the beam bigger, you can decrease the divergence and vice versa. And essentially, there is a lot of formulas here that I'm just going to basically not talk about, because I want you guys to capture the main physics. But the main idea is that you want to make this number as small as possible. You want to make the product of divergence times the size. And there's actually two products. One is in one dimension and the other one in another dimension. And that defines essentially how close your source is to diffraction limited source. You want to make that as small as possible. But the product cannot be as small as possible. There is still uncertainty principle that tells you that there is a quantum mechanical limit to that product, right? It's momentum times, delta P delta X is equal to h bar, basically the same argument. And then you can define the brightness that all these curves that I showed you. And people sometimes use brilliance. I think it comes from German word. It means exactly the same thing. So a lot of people get very confused when I hear brilliance and brightness, and they don't know what the differences are. It's basically the same term. It's the total flux, how many photons you have per second. But it's normalized to this product of the dimensions of the beam in x and y and the divergence of the beam in x and y to the total emittance phase with some prefactor 4 pi squared in this case. The main idea is that if you can make emittance smaller, you can increase the brightness. So one of the reasons that why LCLS is bright, in addition to the fact that it has short pulses and has more photons per pulse, is that it also has very low emittance. It's basically almost diffraction limited. For many X-ray wavelengths, it is diffraction limited. And the reason for, and this is sort of a very basic slide that you probably, I'll try to skip over that very quickly, but the main idea is that this is basic explanation how you generate those X-rays. Essentially, it's a very long undulator. At APS, at storage rings, we don't use very long undulators, and the source size is basically limited by expansion of the bunch of electrons as they go around the ring many, many times. And so that's one of the reasons why the electron bunch, is much bigger than you can create in a linear storage, in a linear accelerator like SLAC. And in this case, you have all of the electrons essentially radiating coherently, and that's one of the reasons why you have such high brightness in the source. And sort of another way of thinking about this 10 order of magnitude increase is that in X-ray free electron laser, if you think about sort of this is progression of different types of sources from the bending magnets to something called wiggler, which is roughly, you can think about this as first generation, second generation, third generation synchrotron undulator. Undulator, the idea is that you can make more magnets and you scale, the brightness scales as number of magnets squared, but it's still times 1 current. But in X-ray free electron laser, the brightness is going to be proportional to current squared rather than the current or charge squared. And that's why you get such a huge boost in terms of your brightness. That's another way to sort of think about the scaling parameters that make X-ray free electron laser so much brighter than a traditional storage ring. OK, one consequence of this brightness. So who cares about this brightness argument? Or who cares about the emittance? One consequence of the emittance is that if you want to focus your beam, and let's say you have a beam that is partially incoherent or partially coherent, which you can think about as many, many different volumes that each of them is individually coherent within itself, but there is little phase relationship from one part of the beam to the other. When you try to focus that beam, and let's say you have a perfect optic somehow, which is often not the case, but if you had a perfect optic, it would still not focus to the point. You would basically just image that source. And if the source is large, you would have an image here that is also pretty large. And so a lot of people, what they do is they say, well, I'm going to make my beam smaller, and I'm going to create a virtual source, and I can focus it to smaller size. But if you have a low emittance, which means that you can have large beam but very small divergence, almost parallel beam, then you can focus it to essentially a point. And because the emittance is limited by uncertainty principle, you will have if you focus something that is diffraction limited to begin with, you're going to get down to basically a fraction of the wavelength if you had a perfect optics to do that. Of course, not all optics is perfect. We're still, in many cases, limited by the optics. But it's still, if you want to do any kind of imaging with lenses, you want your source to be as diffraction limited as possible. And that's another important thing to keep in mind, that LCLS is basically diffraction limited storage. That is, if you wanted to focus it, you can get to as small size as the optics allows you. So the coherence, and I'm going to talk mostly about spatial coherence. Spatial coherence means that if I walk across the wavefront here and ask myself normal to the direction of propagation, this is wave going this way, and if I walk normal transversely to the direction of propagation, ask myself, if I know the phase at one point, how's that related to the phase somewhere else in transverse direction? There's going to be something called coherence length that tells you how how far you have to walk in this direction before the phases basically become uncorrelated. There's also something known as longitudinal coherence, which is basically the same question but walking along the direction of the propagation of the wave. How far the phase is correlated if you walk longitudinally. And I'm going to skip through some of this math, but you can actually derive this as a simple geometry. If you have a size of the source, sigma x and sigma y, this was supposed to be y, by the way, then you can define coherence length as something that is related to as a wave goes as wavelength divided by the angular dimension of the source. So if your distance r from the source, this is going to be a coherence length. That's going to be defined by how far I have to walk across in this direction along x or y direction before the addition of the phases from two different points here, sigma x apart, are going to start adding somehow out of phase. And you can do a simple calculation. It's simple geometry of looking at what's the path length difference if I walk along this direction from two different points here at the source. And so essentially, you can derive this, what is known as coherence lengths, and you can select what is known as coherent volume, which is the dimensions of sigma x by sigma y. And at LCLS, your beam is almost fully spatially coherent, so your coherence length are essentially almost the size of the beam for most cases. But in many cases, it's not the case, and so if you calculate now coherent flux, which is the flux in the coherent volume, it's going to scale as brightness. And so everything, and that makes a very important connection. So when we talked about brightness, these curves that I showed you, brightness or brilliance, where brightness was increasing, everybody wants to have as bright source as possible. If you increase your brightness for the same wavelength, you automatically increase the amount of coherent flux that you have. That is, if I select a single coherent volume, a single mode, coherent mode in my beam, the number of photons that I can work with will scale linearly with brightness. If I increase brightness by a factor of 100, I automatically get 100 times more photons. OK, so I wanted to talk about now, this is sort of the primer about coherence, and we're going to talk about something a little bit more. But I wanted to highlight two specific techniques that are actually used here at LCLS, and the techniques that I use in my lab. In my group, X-ray photon correlation spectroscopy, which allows you to look at coupled to nanoscale fluctuations, and I'll try to explain to you what that means in a little bit more detail. Another technique, which is coherent X-ray diffractive imaging. It has sometimes several different names. Lens-less imaging, you may have heard about that. And the idea here is to do real space microscopy based on the phase retrieval, based on essentially reconstructing the Speckle patterns that I showed you earlier, Speckle patterns like that. OK, so first, let's try to get you guys waking up a little bit. So this is the laser speckle. I actually took this picture in my office. So if you take the laser and just shine it through something that is a little bit opaque, like this cup, I will get a speckle. So those of you who are sitting very close in the front row, you can actually see this speckle pattern, right? So this is the manifestation of the fact that you have defects here, some roughness of the plastic. And as the beam goes through, it scatters from all these imperfections. At random amplitudes and phases, it adds up to this speckle pattern that you see here. So the question I wanted to ask to the students, not the faculty, to the students is, when do you think was the first time that the visible light speckle was observed? Just a decade, roughly.
60s.
So what is it? Speak up. Again. Laser. So when was the laser invented then?
The laser is like the 50s.
50s, well, 60s, yeah, 1960, technically. So a lot of people say 1960 because they think that you need a laser to do this. And it turns out that it's wrong. And the answer is actually about almost 100 years before that. So the first speckle was detected by Carl Exner. He was using candlelight, and I'm going to come back to explaining why that is. But it was such ancient times, he didn't have actually photographic technology, so he had to sketch it in a notebook. So make good sketches, because someday, 150 years from now, somebody's going to show your notebook in a slide. So he sketched these speckles. Probably other people have seen this too, but they just didn't make a good recording of that. Then von Lau, the same von Lau who got Nobel Prize for X-ray work, has been also using arc discharge lamp to produce these beautiful speckles from some powders. In any case, so this is kind of weird, right? So how did they get all this? We know that you need coherent light to produce the speckle, to produce this interference patterns. How is it possible that they were using candlelight? We all know candlelight is a very incoherent light source. I'll explain this in a second. But does anybody know the answer? Maybe somebody knows the answer. Yes, how? Small angle, yeah, so something like that. So basically they can filter the light. I'll show you the slide which explains this. But in fact, in fact, you could argue that speckles were observed even before that. So when you guys were like 2 years old and you look up at the stars and you see twinkling of the starlight, that's basically a speckle experiment. Because what happens is the light is so far away, the angular dimensions are so small that the coherence length is large enough to interfere across the atmospheric density fluctuations that happen in Earth. And so then your eye becomes a point detector that sees bright and dark fringes passing through it. The speckle pattern changes as the atmosphere changes around. And so that's why the stars actually twinkle. And the planets do not. And so that's how you can tell actually the planets are much bigger in angular dimensions and the coherence length becomes much shorter. And so this is a big nuisance for, the speckling is a big nuisance for astronomers. Because when they want to detect a planet around the star to find what other Earths are there, they always have this speckle around it unless they go to space or use some sort of aberration techniques, correction techniques to correct for all these distortions caused by atmosphere. So it's kind of ironic that for astronomers this is a big nuisance. For X-ray physicists this is a great tool, right? So we're sort of turning things around. So in fact, Newton has been actually talking about this twinkling of the stars, and he actually figured out it basically has to do with the speckle, basically the speckle phenomena. Okay, so let's go back. So how did these guys, Exner and von Lau, how are they able to create a coherent light source out of incoherent light bulbs and candles? Well, the idea is that if you make it spatially coherent, if you create a virtual source by, let's say, putting a filter here and selecting, so remember that when we talk about incoherent, it just means that the coherence length is very tiny, right? The wavefront is not a plane wavefront, but it has many, many distortions. But if you put a little filter, if you put a pinhole in a screen, it will select a region of your wavefront that can be approximated as almost a plane wave. And then far enough away, you can also think about it as you create a virtual source far enough away from the virtual source. The spherical wave here looks almost like a plane wave that you would expect from the laser. Right. And one trick is, of course, not only you have to make it spatially coherent, which is what I'm mostly talking about, but you also have to make it temporally coherent, meaning that you want to select a single wavelength. In fact, one of the reasons why Exner's speckles were all stretched out is that he had actually many different colors. He filtered it spatially, but he did not filter candlelight temporarily. So he had all the different colors creating speckles at different angles. And so that's why his pictures were all like stretched out speckles. But he could see the colors everywhere, basically. If he used some sort of prism or some sort of other temporal filtering techniques to select a single wavelength, then he would have seen much nicer speckles similar to the one that you see with the laser. So basically, if you combine the two, if you spatially and temporarily filter your light, you pay a huge price by throwing away a lot of photons, but you can create a light that far enough away looks like a coherent light source. And that's basically how the first X-ray speckle was observed, probably before many of you guys were born in 1991. By Mark Sutton at LCLS, which is the second generation synchrotron, not even the third one. In fact, many people did not believe that it's possible. They thought he was looking at some grains in a metal or something like that. It's not. They thought it was a texture, not a speckle. Okay, let me kind of switch gears a little bit and tell you something else that was on my mind a lot. So in the Institute of Physics actually polled a number of readers about what's the most beautiful physics experiments of all time. And so these are the submissions. Number one was Young's double-slit experiment applied to interference of a single electron. And it turns out that, we all read, and you can read some of the other ones. They're all sort of classic experiments that are really beautiful and really fantastic in many ways. But this is the experiment where, if you remember from reading Feynman's lecture Physics, where you can send one electron to diffract through two slits, and you're looking at interference pattern behind it, and you see that interference pattern looks like it's a wave rather than a particle. And the real sort of twist that Feynman likes to give is that even if you send one electron at a time, right, if you send many electrons at the same time, you could argue that they still somehow bounce from each other or interfere with each other. But you can even send one electron at a time, and the pattern is consistent with what would happen if an electron went through both slits at the same time, right? And if you try to figure out which slit it came through by doing additional observation, you actually ruin that interference, right? So you change the experiment by modifying it. So the idea of this experiment in the Feynman's analogy was thought experiment that if you send any particle, it could be a light particle, but in most cases people like to use electrons. Electrons basically think about it as almost as tennis ball. It manages to go through both slits at the same time and create a pattern that has these fringes instead of just the shadow mask of this object. And so that's a quantum mechanical, that confirms quantum mechanical nature of an electron or light for that matter. And so it turns out that if you look at the history, that this experiment with a single electron, sending one electron at a time and collecting this data, actually has not been done until much later after Feynman talked about that experiment. People have done other variations of the experiment that indicated that would be the case, but actually haven't done that experiment that he describes in Feynman's lectures. And so this is the experiment. It was done only in 1989, way after Feynman was talking about this. These are these many fringes that people observed in this electron diffraction experiment by making the electron go in through two slits and sending one electron at a time, but they would see that they would collect them in this fringe-like patterns. And so why am I talking about this double-slit experiment? Well, because the Speckle experiment is basically exactly the same experiment but with light. For the most part, we send one photon at most per pulse. The interference with complex sample that we put in our beam, and so that one photon interferes with itself throughout the entire sample and forms the Speckle pattern. So essentially, we build it up one photon at a time, one photon per pulse, or 0 photon per pulse in most cases. And so you can think about this as basically verifying quantum mechanics, millions of times a second, and while you're collecting the Speckle pattern at normal storage rings. At LCLS, it's not going to be the case because you're going to have many more coherent photons per pulse that you're going to detect in your detector. OK, so let's talk about XPCS. What is this XPCS? X-ray photon correlation spectroscopy. I'll introduce this technique really sort of quickly. If you know about light scattering, dynamic light scattering, that's basically the same technique but taken to X-rays and given a slightly different name. The idea is that if you have a variation of combination of particles that all scatter, contribute to the far field Speckle pattern, this interference pattern that created by these many different particles. If the particles start moving around, then the interference pattern will change, right? So this is just like if I start moving my glass through here, I'll change the diffraction pattern. I'll change the Speckle distribution because the relative phases and intensities added from different scatterers will change. So think about this as not a double-slit experiment, but 100-slit experiment, 100 pinhole experiment. And if I change the positions of all these pinholes, I'm going to change the Speckle pattern. I'm going to change it at the same rate as I'm changing the sample. So therefore, if I simply sit at one pixel here and I look at the fluctuations of intensities, I can correlate them in time. And that will tell me that the correlation function here means that at very short times, the intensity does not change, and it's correlated with itself if the delay between the two measurements is very short. But if I change the delay to very long times, the intensity at one time is no longer correlated with the intensity some time later when the delay is very long. This decay of the correlation function tells you that the system changes and decorrelates in real space at that time scale. And since you can measure that at different wave vectors, you can learn about how the system is correlated across many different spatial frequencies. So for example, in a Brownian diffusion case, you can actually measure the fact that the displacement is going to be scaling the square root of time because you can look at different q's and figure out the time is going to go as q squared that you measure here. So this is a very powerful technique because you can measure all the different q's at the same time by simply correlating the speckles. And so this is one such quick example. You could calculate something known as intensity autocorrelation function. If you know what autocorrelation function is, great. If not, that's fine. You can basically just think about this physically as how long does it take before the system changes to a new configuration. But you can define it mathematically like that. And you will see that the autocorrelation function will decay, and the time at which it decays, this exponents, the exponent in time will change as a function of wave vector in most systems. That means that the system sort of decoheres at different length scales at different times. And there is a little bit of internal sort of baseball talk, inside talk about speckle contrast, stretching exponents that you don't have to worry about it too much in this slide. But if you're interested to learn more, you can ask me later about that.
So,
yeah.
Back to this slide here.
Yeah.
I can read the cues from here, but what decoheres quickest?
Well, so so if you think about looking at the system in a microscope in real space, right, you would see that at short distances it will decohere the fastest, right? And then if you zoom out and look at sort of low resolution image, it will take longer to decohere. So usually the small distance, which is the large Q, will have the fastest dynamics. In fact, I don't know if I have this. Well, I don't think I have it in this movie, but I had some movies where you can actually see it by looking at it by eye. You can kind of judge by eye. So the typical experiment is the way we do this at storage units is very simple. We just take snapshots at different times, and then we correlate intensity in the same pixel with itself sometime later, and we calculate autocorrelation function. And you can see by eye, you can see that they become decorrelated, but this is very slow time scales. In fact, this is basically, in order to see this by eye, we're looking at a very slow response in a matter of minutes and sometimes even hours. Here's one example. We can see it by eye a little bit better. So as we change the temperature, this is a magnetic system that has a spiral-like structure. And by looking at the speckle patterns, as we approach essentially a phase transition, you can see that speckles here sort of almost don't fluctuate, and then speckles here begin to fluctuate quite a bit. And this is more or less real-time moving in a helical holmium system, right? So if you just simply stare at some region here, you'll see that speckles change very rapidly, whereas maybe at small Qs, they don't change as quickly. Maybe that's not the best example. So this has been looked, this technique has been applied to a number of different systems, mostly very slow systems, and I'll try to explain basically glassy dynamics. But people have looked at a number of hard condensed matter systems, spin charge ordered states, soft matter. That's where you have a lot of glassy systems. If you mix colloidal particles, you can basically make your dynamics go very slow, and then it's perfect technique to study that at very small length scales. There has been application in biology and, of course, material science and so on. But if you look at sort of where, in terms of the time or frequency or energy, if you will, versus the wave vector, where this technique has been the most successful, this is essentially S of Q omega map, right? So when we look at different processes, we always, in physics at least, we like to describe it as S of Q omega, which is basically the length scale goes into Q, the time scale goes into frequency. This is a nanoscale, but very slow processes measured so far. So anything that is larger, you can measure with various light scattering technique, either dynamic light scattering, or maybe if you want to go faster in elastic techniques like Raman and Brouillon scattering, or you can also use an elastic neutron or X-ray scattering or spin echo to measure faster processes if you want to have a high spatial resolution, but not that you cannot get with light. Yes?
So in your previous two slides, the images you showed, that surface measurements or like...
In this case?
Yeah, like how deep are you looking?
So basically, you're looking at whatever X-rays. So that's another, whatever the X-ray penetration depth is, you're going to be looking at more or less, in most cases, you're going to be looking at the entire, penetrating volume, right? So in this case, for example, are you talking about this particular system?
Yeah,
or?
yes.
So in this particular system, these are thin films. So we're looking at basically, these people looked at the whole film. And I'm forgetting now exactly what the thickness was, but it basically tens of nanometers or something like that, perhaps. Yeah, and that could be a good point to make, because with visible light, you would not be able to penetrate through the whole system. So in this experiment, we're looking at about micron, if I remember correctly, on that order penetration depth. So we're looking at domains fluctuating within the first micron of the surface, which is bulk to most people, but some neutron people would say that this is still surface states, right? But it depends basically on your energy, X-ray energy, and your penetration depth in a particular system. In some other cases, in fact, in the previous system, we're looking at surface fluctuation. So we're in the grazing incidence, so we're interested in surface dynamics. In that case, all the signal comes from distortions of the surface waves in polymer systems, for example. You can optimize the geometry, and you can optimize the X-ray energy and other things to tune that to, to measure exactly what you're after. In fact, I would argue that in some systems you may want to go away from. So in this particular system, it's actually kind of surprising that the spins fluctuate so rapidly, given that it's a thin film system. Surfaces themselves are big defects, and they tend to pin spin fluctuation. So you really need to go to the bulk type systems in order to study that properly. Okay, so the point that I wanted to make here is that actually if you look at most of the systems that have been studied, the fastest ones, the largest Q ones are usually the slowest ones, and these are around Bragg peaks. These are typically liquid crystals, the fastest ones, systems that people have studied with XPCS. And there is a whole bunch of soft matter systems, polymers and colloidal systems that have been studied, but they're all very slow, right? So that's the main point that I wanted to make here. We're talking about ultra fast. This is ultra slow processes, right? These are seconds and slower, or milliseconds and slower. So the question that we would like to sort of pose is, can we actually bridge the gap and use XPCS in this regime where LCLS operates? Can we measure things that are nanoseconds, picoseconds, maybe even femtoseconds with XPCS, and then you can overlap in some ways within elastic X-ray scattering. And maybe I'll skip this slide briefly in interest of time, but one interesting thing about XPCS as you go faster is that the signal to noise for XPCS goes as total flux, but times square root of the time that you measure. In other words, if you and I'll come back to explain this in a little bit more detail, but it means that if you increase the brightness of your source, you can go quadratically faster in time. Not linearly, not square root, but quadratically. So if somebody gives you n times more photons in terms of your brightness of the source, you can measure n squared times faster dynamics. So bridging those orders of magnitude in temporal resolution may not be as crazy as some people think. So there is a setup here. There is XPCS, beamline, LCLS, and the idea that people have proposed, and I should say that right now it has not been hugely successful, and I'll say this because I think maybe it's up to some of you guys to actually figure out how to do this properly. But the idea is the following: you want to send a pulse. Ideally you want to send two pulses, and you will correlate what happens at one pulse with what happens in the second pulse in XPCS. And so you start with a single pulse and you split it off using the split and delay line so that you create essentially two pulses that all come from the same original pulse. And by changing the delay between the two pulses, you can probe dynamics at the time scales that corresponds to the time delay between the pulses. That was the original idea. And if you work in if you come from the optics background, you will say, well, this is sort of trivial. Any undergrad in the lab can just build a whole bunch of mirrors, and you can build that split and delay line in an hour, right? But if you come from the X-ray community, you'll know that aligning one crystal to get a Bragg peak is quite challenging. So a lot of my work used to be done on studying liquid surfaces where you have to tilt the beam down to the horizontal surface, and we use something known as steering crystal, and to align that takes forever. It takes a day sometimes to align it properly and make sure that it steers over the whole range of angles. But in this case, you have, in this geometry, the way it's shown, you have 6 crystals plus all this, well, actually, it's 8 crystals, I guess, if you include all these crystals that have to split it halfway and recombine the beam again. And that becomes very challenging. Also, if the energy fluctuates or the intensity fluctuates, the whole system becomes out of alignment. So for now, this is still a sort of a work in progress. Yes?
Some sort of a dichroic mirror, a beam splitter.
I'm sorry?
Is a beam splitter some sort
So
of...
the beam splitter is, you can think about it as a very thin Bragg crystal that wants to diffract some of the beam but transmit some of the other beam. If you make your crystal...
You had 2 separately colored pulses. Some sort of a dichroic.
Maybe I cannot hear you very well.
Yeah, why are the pulses different colors? Like,
no, they are basically the same color in terms of wavelength energy. Just to illustrate here that these are 2 different pulses. One is ahead of the other one. Sorry, the color here does not mean to illustrate the different wavelengths. In fact, actually, there are setups where you can change, we can offset them slightly in the energy, which is used for something else. But in this case, you want them to be at exactly the same wavelength, more or less. Yeah.
So you assume that the pulses are still coherent?
No, so you don't need coherence from one photon here to have any phase relationship to the coherent photon there. What you need to have in XPCS, that's generally not the case. So again, reminder, so if we send one photon, it's just this double-slit experiment. We send one photon and one electron. It interferes through that system and it forms its own speckle pattern. And then the next one that comes in, it has no relationship to the previous one. It just forms its own speckle pattern. But if the system has not changed, it's going to be the same speckle pattern. So in this case, you don't need to have phase relationship between the two pulses. You just want to split them off and have one, but each of them has to be fully spatially coherent with itself, and the angles have to be collinear, and they have to hit this exactly the same part of the sample. So your sample is going to be here, and then you're going to form speckle pattern here. First one is going to be coming from the first pulse, and then the second one is going to be coming from the second pulse. But you don't try to add them coherently. You just add intensities, basically. So but then there is a question of how do we correlate those two pulses, right? So there is no detector in the world. If you want to offset this by maybe picoseconds or maybe up to nanoseconds, but there is no detector in the world that can read out the whole area detector and then measure the next pulse again. Right, so the whole idea of correlating, measuring two different sets of speckle patterns and then correlating them seems to be hopeless, even if you can fix that. This is sort of engineering issue, right? But then what about the detector part? And here, the answer comes from the fact that you have to remember what is the visibility of the fringes. So if I have fully coherent source, or very close to fully coherent, I'm going to have very high visibility, maximum to minima. But if I add two patterns that are basically not coherent with each other, I'm going to reduce that visibility. And here you can see it washes out completely. You don't see any fringes. So visibility of fringes basically is related to how coherent or how similar the two speckle patterns are. So if I go back here, there's going to be a speckle pattern created by the first pulse, and it's different, perhaps, speckle pattern created by the second pulse. If the system has not changed, the speckle patterns are going to be exactly the same. You just add them on top of each other. The visibility is not going to change. But if system has changed during that time, then the second, the second speckle pattern is going to be different from the first one, and so maxima and minima start to wash out, just like they're washing out here when you add two different coherent volumes together. And so the idea is that basically what you can do is you can just simply look at the visibility, and if you change the system in time with longer delay and the system evolves to some different state, you're going to reduce the visibility of the fringes, as you can see here. The maxima and minima will start overlapping between the two different pulses. Yes?
Could you please go back for another one? Yes. So you are splitting here your beam and reflecting it with 3 mirrors that are, as you said before, are never ideal.
Yeah.
So you have, as I would say, 2 very different pulses that aren't they too much?
They're different in what sense, right? So they're different if the photons in the first pulse look like if this pulse is coherent by itself, it has a spatial coherence, meaning that it has a flat wavefront, planar wavefront, that will create a speckle pattern. And then the second pulse, it could be actually even slightly different intensities. We don't care about it too much. We can normalize for that later. But as long as it's also spatially coherent with itself, and the two pulses follow the same path, that is, they see the same sample from the same angle, that's the only thing that matters for this experiment. Because in the end, we're going to add up intensities from the speckle pattern created by this one with intensities created by the speckle pattern from the second one, and we're going to see if they will smear out the fringes, smear out the speckles. That's what's important here. Does that answer your question? Okay. So the main idea, maybe I'll just skip over some of this technical stuff, is that you can look at the visibility, and the visibility is going to change if the system changes. Yes?
I actually have a question on the side before where it washes out.
Here?
That one, exactly. So that only happens within the pulse duration, right? So if the first pulse is coming in and has like 150
No. So basically, think about.
The second pulse is like 500 femtosecond delay.
Yeah.
It doesn't interfere, right?
It doesn't interfere. You add intensities. And so what will happen is, so let's think about it maybe graphically, right? So if you imagine you have fringes from one pulse, this is your speckle pattern. This is the line cross-section through first speckle pattern. And then you add a second speckle pattern, and you add intensities, but that one, something has changed, and the system has evolved. Let's say it's 100 picoseconds later. And the system have evolved to a different state. It will have some other random speckle pattern that will look like this. And then you add the two together, and you'll see that maximum and minimum no longer match up, right? And so you washed out your visibility because the two are different. So basically, the idea is that, and people have used this in light scattering regime quite successfully, is that looking at the visibility, you can detect the same thing that you measure with the correlating pulses. So in other words, instead of correlating intensities and calculating autocorrelation functions, you can also just simply look at the visibility of the fringes. But then you can ask yourself, OK, but most of the time you don't even have enough. What if your signal is so weak you don't even see the fringes? It all looks like noise. You can do something even better. You can just simply look at the double counts, or the triple counts. In other words, if you look at your detector and you collect, there's going to be some photons that will scatter only once. There will only, not scatter, there will only, some pixels that will only record one photon hit. What you have to look at is how many pixels will record two photons coming to the same pixel, or the same speckle. And it turns out that the ratio, the fraction of these double hit events, which is very unlikely, it goes the square of this, will be different depending on whether the system is in the same state and it's the same speckle, or whether it's two different speckle patterns. And again, you can think about it in that simple picture, is that if everything is fully coherent, you have fringes, which means that some regions, some pixels will have more probability of capturing the photon than in the dark regions in between. If the system is fully incoherent, you add in completely uncorrelated speckles, you will no longer have that's no longer the case, and you're going to have photons more or less evenly distributed in terms of their probability function across the detector. So by simply looking at where these two photon events happen, this is essentially the two different regimes, fully coherent, fully incoherent. By doing this measurement, you can get the same information as can be obtained from autocorrelation functions.
If you already have a low count rate for the single photon process, because that's what you say right now, a lot of background, then essentially you almost never have any double.
Well, so the number of doubles goes as square root of the number of singles, typically, right? So if you have only maybe, I don't know, let's say 1% of capturing a single photon, then you have 10 to the minus 4 probability of capturing a double. The nice thing is that you only need to measure, so then the question is how many doubles do you have to collect? And in order to tell the difference whether it's fully coherent or incoherent, you need something like, to zeros approximation, you need something like, the ratio between the two is 2. So if you measure 20 of them, 20 doubles, you should tell from your statistics of singles whether it's coherent or incoherent. If you want, of course, better error bars, then you have to count more. Yeah.
So along the same lines, that depends on your normalization of G2.
It depends on normalization. So let's talk
statistics of the
exactly.
normalization.
The statistics, well, you know the statistics of singles. You have to measure singles too. You have to know how many total singles you have.
But you need to know from the two.
Yeah, but you know basically so statistically you know the distribution functions for fully coherent and fully incoherent. It's polynomial and something else. I'm now forgetting. I think I have a slide on that somewhere. But you know the two distribution functions, and the ratio between them is roughly 2.
I'm asking a slightly different question. So in your definition of G2 here,
yeah, I think
you assume that the two pulses are exactly equivalent.
It doesn't matter. Actually, the normalization is basically becomes. So let's just. I think this slide is actually going to answer your question. So if you think about a measurement where you have time going this way, and somehow your detector is. Imagine that your detector is super fast, and that as the photons come in, you're always trying to figure out where they are, and then instead of correlating within the same pulse, most of the time you're going to get single hit, right, somewhere in different times. But then sometimes you're going to get double, which is what you need for XPCS. For XPCS, you need to correlate something that happened at one time with something else that happened at some other time. If you think about this in low count rate, the only time that you don't get 0 here, when you correlate this along the time dimension, right? For a single, it's going to be 0 all the time, because one of the intensities is going to be 0. The only time that you don't get 0 is when you have a double, and also triple and quadruple events. But let's forget about those, because those are even less likely. So effectively, in G2, you can think about this as a number of doubles, how many doubles you capture. And then this becomes number of singles squared or whatever. There is some renormalization that you have to worry about. But basically, this is just total intensity. What's the probability of getting a single? And this is the probability of getting a double. So if you simply count your doubles divided by total count of singles, which is total flux, it should give you a measure of G2 to zeroth order approximation, because there is also triples and so on. And in fact, you can simulate that, and we've done this in my group, and it basically scales. If you calculate using the traditional XPCS autocorrelation function versus just looking at doubles versus singles histogram, it basically scales exactly the same way. The only difference here is some noise due to the fact that well, first of all, you don't count the triples in this case. So there will be a small correction for that. And also, there is slightly different binning parameters, but it basically measures exactly the same thing. So the bottom line is that in this measurement, you can just simply look at the number of doubles. So if you measure this ratio of doubles versus singles here, you should be able to look at the histogram. You should be able to figure out what the contrast in your experiment is without doing any additional autocorrelation. So it is possible, assuming that, yeah.
Are you obliged in this case, for example, to take only single shots? Or can you average, for example, over those who have the same?
You can average. So each time what you measure is basically what's shown here as beta is the degree of coherence in your overall measurement, right? So if you add too many, so if you started with beam that is fully spatially coherent, which beta equals 1, and you just measure a single shot and nothing happens in that one shot, it's too fast, then you're going to measure the speckle pattern that will have contrast of 1. Means that the maximum to minima is going to be 0 and maximum is going to be some value, maximum value. But if something has happened during those, let's say, 100th second of the duration of the pulse, which means that the speckle is already being decohered by the changes in the sample, your beta will drop towards lower values. And if it's decohered completely, it drops to 0. You can also think about just adding 2 different snapshots, right? And if the system has not changed, you should get the same value, ideally 1 if you started with 1. But if system has evolved, then you're going to change the number. It's going to drop down. You can only decrease, usually, the correlation value. So think about this as a visibility factor of your fringes or your speckle pattern. And again, so the main point here is that the drop-off of this visibility. So here, for example, you can see that for the triple case, you can see it even more clearly that the beta here is 0.276. That's you measure it by fitting to the line. This would be what the number of triples would be if beta was equal to 1. This would be completely uncorrelated 0. And so in this case, this is actually an experiment done at LCLS. I forgot to put the reference here. But in this case, they basically froze the motion or partially froze the motion of the atomic diffusion motion in a liquid metal. And they could measure the contrast here using that technique. They could just as well measure it by looking at the doubles instead of looking at the triples. In this case, they had enough triples even to actually measure that. OK, so I'm actually going a lot slower than actually, this is one thing that I wanted to show just kind of as a fun thing. So this is the same group that measured this. So they're looking at metallic glass palladium nickel phosphorus. This is early measurement. You have to always be aware of the damage that your beam can do, especially at XFEL. They were basically drilling holes in a metallic glass, which is quite impressive, at least if you ask me. So this is the crater that was left after the beam was exposed to this metallic glass. Yeah?
I do have a question here. So you only create these craters if you focus the beam.
Well, in this case, yeah, this is done.
Do you necessarily need in this technique to focus the beam, or what's the difference between the focus?
So you don't need to focus the beam. The only issue with, well, there are several issues that would not focus in the beam. So the one thing is that ideally you want to match your resolution of your detector to the speckle size. And if you make the beam millimeter sized, then your speckles, the pixels become very, you have to put the detector a kilometer away, or you want to make your pixels very tiny. And making your pixels small is also a problem because of the charge spread out. So there's a lot of technical issues. But in principle, I would argue that you may even want to make your beam as big as possible as long as your detector allows you to, because that means that you're looking at statistical average over a larger region. Right? So you're looking at autocorrelation function of the sample that includes many different regions, and so you perform ensemble average over many, many different particles in this case. You don't want to look, in other words, if I think about focusing too much, at some point you're looking at, let's say, a single particle, and then the fact that you're using coherence doesn't matter. You could just look at the intensity fluctuation from a single scatterer, right? Single domain wall for that matter. So this is the situation that a lot of times people who study, for example, diffusion of defects. You ideally want to have something like 100 or 1,000 defects in your beam. If you're looking at a single one, you no longer have to use the coherence. You can just you can just track it by intensity fluctuation from incoherent beam, if you could focus it that well. Okay, so let me switch some, and I guess I didn't leave enough time, so I'll try to maybe skip some slides, and you guys will have to forgive me. But basically, I wanted to talk about some other part of the coherence that I think is maybe more interesting to some of you, which is the lensless imaging. And so if you're a biologist or chemist, you may ask yourself, well, I want to know not only how fast something is changing, but also I want to maybe image a molecule or some fraction of the molecule. And I'm interested in some process, chemical process or maybe biological process that happens here. So I want to combine microscopy with ultrafast scattering. Can I do that? Or if you're a physicist, again, if you're driving some of the systems that I showed you earlier, they're all phase separated, and you may not want, again, not only know what on average your response looks like, but also what is locally happening at the ultrafast timescales. And this is very challenging, right? So the way I told you, basically, I want to have spatial resolution down to nanometers or maybe even atomic scale, and I also want to know what happens in time domain as well at this ultrafast time. It sounds very challenging. So one approach that I wanted to talk about is something called lensless imaging, with the idea is instead of using the lens to demagnify an object and look at it, what it looks like, which is done in most microscopy techniques, what if you just let the light diffract, eliminate the lens entirely, and then this is the diffraction pattern that you can think about as Fourier transform of your structure in real space. So in principle, if I knew all the phases, I could just invert Fourier transform, and I get my image in real space, right? So that's sort of the simplest argument for that. And it turns out there are algorithms that allow you to do that. Of course, you have phases that are lost during the measurements, so you have to do some tricks in order to recover the phases that are lost. So the question is, so this is sort of an example that I like to use for pedagogical reasons, but it could be anything. It could be a molecule. Imagine whatever your favorite system is that you want to study. It creates a Fourier transform which looks like this. In this case, just so you know, this is a magnetic domains that I'll show you in a second, and it creates a speckle pattern like that. And the question is, can we invert this diffraction pattern? And the answer normally would be no, because we've lost all the phases here. What we measured is how many photons arrive at different pixels, and that's the speckle that we see here. We don't know the relative phases at which these photons arrive with respect to each other. By the way, let me just say one way to figure out the relative phases is to mix in another reference beam, and that's called inline holography. I'll show maybe one slide if I have time about that, but that has some other complications and disadvantages for different reasons. But can we actually do that without mixing the beams? It turns out you can if you oversample it, meaning that if you measure the spatial distribution of intensities that is finer than the dimension of the speckle. So the size of the speckle here is inversely proportional to the total size of either the beam or the object that you're eliminating. So that's called Nyquist frequency. The highest frequency that you see here in Fourier transform corresponds to the largest dimension over which you allow interference to happen, right? So that's the speckle size, corresponds in this case to about 10 microns, the dimensions of our sample, basically, or the beam. And so it turns out that if you measure the intensity variations finer than that frequency, the Nyquist frequency, by at least a factor of 2, in reality by a factor of 2.5 or so, you can actually invert the diffraction pattern, solve for the phases in a unique fashion. And it still sounds a little bit like a magic. So this is my magnetic film that I'm trying to image. This is diffraction pattern. There is no basically lens in the way. And this is just a pinhole that selects a single coherent volume that is about 10 microns in size. Because remember, this is the pinhole that Exner and von Laue would have used if they have an incoherent beam. So the system that I'm studying here, and again, if you're not into magnetism, you can disregard this. But in 10 seconds, I have the maze-like randomly meandering sort of patterns of domains where it spins is either up or down out of the plane of the film. And so what I'm trying to image is these domains. Some of them have one color, let's say, going down. The other one I'm going to call spin up. How do I see magnetism with X-rays? Again, this is a sort of a 10-second hand-waving explanation. You use resonant X-ray magnetic dichroism. So the idea is that if I tune to one of the resonant edges, in this case, we have gadolinium and iron in the system. You can use either gadolinium edge or iron edge. We happen to use gadolinium. If you tune to one of these edges, in this case, we used I believe we actually used M4, maybe M5. So if let's say we pick M5 here, you're going to have two different channels. You're going to have two different scattering cross sections, depending on whether you have the circularly polarized light is either oriented in the same direction as the spin or opposite direction to the spin. You're going to have two different absorption cross sections. This will only happen at the edge. If you walk away from the edge, the two cross sections become the same again. And you can notice that at the other edge, at the M4 in this case, the contrast is flipped. And you can actually use that. And that has to do with the fact that the probability of promoting an electron to the split Fermi surface is actually different, whether depends on basically relative polarization of the light and the spin that you're promoting here. That only happens at the resonance. So the main idea here is that when you tune to the resonance, all of a sudden you see the domains. They will scatter differently. If you're away from the resonance, you don't see the magnetic domains at all. It's just a thin magnetic film. So when we do this experiment, when you tune to the resonant edge, we get additional Speckle pattern. If we're away from the resonant edge, we just see the edges of our pinhole, all attenuated uniformly by the film. We don't see the magnetic domains. And so the idea is, can we actually phase this diffraction pattern that is shown here? Can we solve for what configuration of domains looks like here? And the original phase retrieval paper by David Sayer, which is basically formulates that you can do this, and that comes from the Shannon's theorem. Shannon is the famous scientist who basically dealt with a lot of information, process information theory, who figured out that it's possible to do that. The reason I like to show this to the students is that this is the entire paper. It's not an abstract to like APS March meeting. This entire paper, it has 3 references, and it says the extension to 3D is obvious. And you can ask people who try to do this in 3D whether it's really obvious or not. But basically, he just tells you that if you measure it at fine enough spatial frequency, you can do that. He doesn't tell you how to do this. He just says mathematically there should be a solution somewhere. So how do we deal with this mathematically? Well, what we do is we basically alternate. We have a set of constraints. We have reciprocal space, Fourier transform space, Fourier space basically. Well, we know the amplitudes but not the phases. So I'm going to show amplitudes as color and phases as color and amplitudes as brightness in this sketch. And we have real space constraint where we know that our size of the beam or size of the object fits in some box. And because it fits in some box, that gives rise to the speckle. The speckle size here is the size of the box. That's what we have to sample by at least a factor of 2. And what we do is we start with random phases. We throw some random colors basically on our amplitudes that we measured, the intensities that we measured. We know how to project back to the real space by doing inverse Fourier transform. Because we oversample it by, let's say, a factor of 2.5, this object is going to be bigger by a factor of 2.5. And we also have a lot of other problems, like the amplitudes could be, the densities could be imaginary or could be negative. So we apply the real space constraint where we remove everything outside of the box that we know it fits in, and we may update some, our densities with real values instead of imaginary and so on, positive values. Yes?
Showing like a tychography setup, right?
It doesn't matter. It's the same idea. Yes, I'm showing tychography, so those of you who don't know what it is, never mind what it is. But yeah, I can.
If you have like overlap with wall motion, the overlap is not going to be exactly the same between 2 exposures, right?
So this is general. So this is general for not only tychography, but single molecule imaging for anything. So if you're looking at single particle, this is a general algorithm. So I showed you, actually, I don't think I showed you tychography. In this particular case, it is experiment done using tychography. I wasn't prepared to talk about it too much, but basically tychography is the idea that you can build additional constraint by overlapping 2 different regions in real space. If you have extended object, you may want to do that. But you don't have to do that. In principle, a lot of systems that we study, other people study, don't even use that for single points.
Like if you have wall motion between your overlap, so you have one exposure with the walls in one position. In the second exposure, the walls have slightly changed.
If you're looking at dynamics, you don't want to use tychography. That's my argument. You want to use a single shot approach. We can talk about this later, but I wasn't planning even to talk about tychography too much, even though this measurement technically used tychography. But this idea, so let me just go back to this algorithm is more or less generic to almost anything that any lensless algorithms that people use, where the idea is you alternate. So once you updated your real space image, and it's going to be wrong because you chose some wrong random set of phases, when you Fourier transform back into the reciprocal space, now all your phases are wrong, and your amplitudes are wrong also. And so then you update your amplitudes with the ones you measured, and just keep going into this loop. And it turns out that over time, you basically will converge on some solution that is your solution that you began with. And basically in some mathematical way, you have 2 surfaces. you have real space constraints. The size of the object is finite. And also, perhaps your densities are real instead of imaginary. Maybe they're positive instead of positive and negative. And then you have reciprocal space constraints, which is the fact that you measure the amplitudes, you don't know the phases. There is a solution somewhere here. This is what Sayer's paper basically told you that it exists. Yes, Marcus?
Is there only one solution?
Is there only one solution? So yes, there is only one solution if you oversample by more than a factor of 2 in 3D. In 1D, for example, that's not the case. In 2D and 3D, there's only one solution. But the real answer to that is that even though there's one solution, finding it is a problem. And also the solution is sort of fuzzy because these things are fuzzy because they have error bars, right? So that's always a question that you have to wonder about. Just because mathematically it is one solution doesn't mean that when you do multiple reconstructions, you always find more or less the same solution, but it looks slightly different. But it's around, it looks similar enough. It just means that you arrived at this point instead of this point because this is a kind of a fuzzy surface instead of being a smooth surface. It has an error bar, basically. Anybody who's experimentalist knows, right, that nothing is perfect in life. That's more general, right? So then the idea is that you can start with the initial guess and you know how to project from one surface to the next. And the only problem is that sometimes instead of converging in a solution by these alternate projections, you may get stuck doing this forever, right? And that's why this tychography helps to overcome that. But in many other ways, you don't need that because there are other ways to basically overcome that as well, numerical ways that maybe we'll skip a little bit. OK, so this happens to be a tychographic example of how this convergence happens in a simulation where you throw away the phases and you can recover the face of the famous composer. And you can also do the same thing for our magnetic domain. Since I showed you the magnetic domains, I'll show you this movie. This is iteration. This is how many laps around this algorithm. How many loops have we done? And again, we start with the random phases. We don't tweak anything deliberately. We just let it run by itself. We start with completely random numbers, and then over time, you can see that it builds up some structure that you can begin to see as a sort of real domain-like structure. And you can also watch your something called phase retrieval transfer function, which is basically tells you the error function, and you can see it drop. You can actually figure out how well what you're computing it matches up with what you measured. And that also gives you a little bit of feedback of whether it converges or not. So let me just kind of skip, because I think my time is, I wanted to show a couple of examples of that. So I'm going to skip a whole bunch of my stuff, which is not relevant. You can ask me about that. But the question is, can we actually do this? In this case, maybe to answer your question. So you asked me, what if your domain actually moves during the measurement? And this is a quasi-static measurement, meaning that we look at the domain, we change the magnetic field, so we change the configuration of domains. We do the imaging, and the imaging takes time. It takes minutes to do it. And so if you stare here, you can see that this domain actually jumped during the measurement. That's exactly what you asked me. And you can actually catch that, but you don't know when it jumped. You just know that it jumped sometime during the measurement. That's why we see half of it here and half of it there. So it's a little bit like if you take a long exposure of me talking here, and while you're taking exposure, I jumped here, you're going to see half of me here and half of me there, and maybe some blurry stuff in between, right? So that's basically what we measured here. But the question is, can we actually do this at ultra-fast regime? Can we repeat the same experiment in a faster domain? I'll show you a couple of examples of people already doing that, even though I don't think it's as many examples as I thought there would be. But just kind of to remind you, so this coherent X-ray diffractive imaging could image not just electron density, which is most people perhaps interested in, but it could image other things. And I showed you example of magnetic domains. A lot of us are working on lattice strain and defects. And you can image for electric domains. You can also look at ionic diffusion. So you can measure a number of different physical processes happening in your system. The way you couple to the strain, this is a sort of a simple explanation, is that if you think about periodic lattice planes, if they're periodic, then all the planes would scatter to the Bragg peak at exactly the same phase. That's the Bragg law. But if I started shifting them around, if I displaced them using these arrows, I moved some of these atomic planes this way, and then I started shifting them back the other way, creating the displacement field sort of going negative here. What I'm doing basically is I'm changing the phase at which these planes contribute relative to these planes. They used to be in phase, but now they're slightly out of phase. And what I can measure using the coherent diffractive imaging is that phase, right? Because what you get in your space, in your density, you get your density of your plane as a real part, and the phase corresponds to the displacement is the imaginary part of what you measure. So when you Fourier transform back, now generally you have a complex function where the imaginary part that corresponds to the phases can tell you about the strain in the crystal. So a lot of people are doing that. So what you measure is this, where it's the projection of the strain on the Bragg vector that you're measuring. So let me, I think I'm going to skip some, but this is just sort of examples, again, of quasi-static measurements that are possible. So in this case, we're measuring some faceted nanoparticles, and we can see the split in the Bragg peak that is due to the domain wall, this low-angle domain boundary that shows up. So I'll show you just very briefly a couple of examples. In this case, we're looking at a nanoparticle, and again, using this phasing, we can measure the strain at different parts of the nanoparticle, and we can see that the strain at the corners, for example, is higher, and these two corners is higher than near the flat surfaces, which is sort of consistent with the Laplace pressure that you would expect from the fact that it's a higher curvature here. This is sort of another quick example. So you can get a nanoscale distribution of strain in 3 dimensions. You can slice it in many different ways. People have measured ferroelectrics. So this is a group of Stefan Hrushkevich at Argonne, and then they can measure ferroelectric domains using exactly this technique by using basically the phasing. So I wanted to highlight a couple of examples very briefly. This is my group's work on lithium-ion diffusion, and all of this is quasi-static measurements, meaning that it's not done at XFELs. These are done at synchrotron sources where you can take time to collect these diffraction patterns until you get very high resolution. But let me kind of maybe show you a couple of examples of some ultrafast work. So let me just skip through all this stuff. So this is the idea for the ultrafast work. Has anybody talked about this already or not? Okay, so maybe I decided I should definitely talk about this. So the main idea, one of the interesting ideas that came out when LCLS was discussed is, can you actually do the single molecule imaging using these phasing techniques? And the idea is that if you have a molecule, let's say a single biological molecule, and the pulses is short enough, when the pulse goes through, you're going to create a speckle pattern that is going to be basically interference of all these different atoms. And if you could phase this the speckle pattern, you can go back and retrieve what the single molecule looks like. And the pulse is fast enough that the molecule will blow up. This process called Coulomb explosion, because you ionized, you stripped all the electrons, so now there's a bunch of ions sitting there, and they're going to repel each other and by Coulomb repulsion, and they're going to explode. So the particle is going to explode, but if the X-rays are faster than that explosion process, you can actually you can see what the single molecule looked like before you blew it up. Yeah.
But is that computationally feasible? It
Okay,
like
so that's the key. That's one of the key questions. So right, so this is a big problem, right? So I sort of show this as one slide, and in PowerPoint physics it works great. In real physics it's a little bit more challenging. So let's talk about what are the key challenges here. So it sounds very good mathematically. So first of all, you have to figure out how long it takes to blow it up, and people can use molecular dynamics simulations. And there's a question of how well do we know about these processes, because I would argue maybe we don't. But it tells you that if you're below, let's say, 10 femtoseconds, if your pulse is short enough, maybe you can do that. And some people are saying that it's below 1 femtosecond. I'm actually not working on this field myself, but maybe that's changing every day as we speak. One challenge, sort of physics challenge, is you have to make sure that there is a particle waiting there, sitting there waiting for the beam to hit it, right? And so the injection of molecules is a separate technological problem. How do you inject them? Ideally, you want to inject them enclosed in a water or some sort of aqueous environment like helium or water droplet, so that you're looking at a sort of natural state of that biological molecule, not some dried up molecule, right? But that's one challenge of how well can you time. You only have 100 pulses per second. How well can you make sure that there is a particle there when the pulse goes through? The other sort of, so the computational challenge, and again, this is one of the sort of most beautiful mathematical ideas that I've heard in a while, but I think it has a lot of challenges ahead, and maybe one of you guys can actually help us solve it. By the way, I believe that this is going to be possible. It's just a matter of getting the time. So the problem is that if you don't have enough statistics, you're going to get a very noisy diffraction pattern, right? You don't have the luxury of the way we do it, just collecting many, letting your samples sit there and collect your data until you're satisfied with the quality of the diffraction pattern. Most of the time, you're going to get a very noisy diffraction pattern. And the diffraction pattern that you're going to get is only the Ewald sphere projection through your three-dimensional Speckle, Fourier transform. So you have some three-dimensional Fourier transform of your molecule electron density, and you're going to get a projection in a single measurement, right? You're projecting that depending on the orientation of the molecule, where the Ewald sphere will cut through that your Speckle ball in 3D. And that projection is going to be very noisy. And so the question is, if you inject this, well, you could say, well, I'm going to do this experiment again, but I'm going to inject in the same molecule again. It's going to get a different orientation, though, right? I can't control orientation very well, so it's going to be a random orientation that I'm going to expose it at. And mathematically, you could argue the following. You could say that all of these projections, random projections, they're going to go through the center, through the q equals 0 point. And if you know one of these, maybe perhaps noisy diffraction patterns, and there's going to be a different, let's say, consider a different random orientation of diffraction pattern that slices that Speckle ball at a different angle, they're going to have a common line here somewhere. And because you have a common line, you can maybe try to stitch them together mathematically. You find the line that has the highest degree of correlation in those diffraction patterns. And so you say, well, I know now these two of these diffraction patterns were taken. I know there is one common line there. I don't know. It's like a hinge now. I don't know what the relative angle is. But if you took the third one and you find the common lines between the first two, then it allows you to sort of fix them in space. And perhaps there is a big uncertainty in finding each one, but then you keep doing this experiment at different angles. And if you are very good at classification of the diffraction patterns, you have to understand what they look like. And doing this orientation in reciprocal space, perhaps the hope is perhaps you can actually stitch them together to get a full three-dimensional image. And again, it sounds good mathematically, but experimentally, we're dealing with the diffraction patterns that are super noisy, right? There is no, we're trying to image something that is mostly hydrogen and carbon, right? And doesn't scatter very much. And it's tiny little molecules. And so doing this is a very challenging. And you're not satisfied until you get an atomic resolution, right? It's not like when I image magnetic domains, 30 nanometers maybe is enough, or 10 nanometers maybe is enough. Here you want to have atomic resolution, otherwise it's not useful, right? But this is a very challenging approach, but it may still work. There is a lot of other, again, technical problems and technical difficulties that have to be overcome here computationally, technically, in terms of detector development and so on and so forth. But this could be an interesting development. OK, let's actually show you a couple of examples. I have like 5 minutes, so maybe I'll skip. Well, this is what we, this is sort of one of the first demonstration of this ultrafast imaging, where you destroy the sample with one shot, but you can get an image. This is, in this case, the image is sort of artificial image. And this is basically when there was a summer school here 7 years ago. This was, I think, was widely circulated as sort of state of the art. So you can etch something in a silicon nitride membrane. You can blow it up, and in a single shot, you get a diffraction pattern like this. It's already, after this shot goes through, it melts the whole membrane, so it doesn't leave, it no longer exists. This pattern only sees the beam for whatever 100 femtoseconds. But reconstructing the single pattern can give you a reasonable outline of what the sample looked like. So you can, in principle, you could maybe use this as this probe and destroy type methods. So what has happened since then? And this is not a complete study, but one of the, I think, exciting results of this lensless imaging that are based on coherence is the single mimivirus particle imaging that was done here at LCLS. And the idea is basically phasing these diffraction patterns and looking at two-dimensional projection of different but supposedly identical versions of the virus. And you can learn about this sort of internal structure by doing this phasing, using this phasing algorithm. So this, I think, is the best. Maybe somebody can tell me if there is even better example of this phasing approach. But so far, this is, I think, one example of how this spatial coherence and lensless imaging could be used at the free electron lasers to get some of this information. By the way, I think the second author here was from Uppsala group, was a student here 7 years ago. So it's kind of another good example that people who come to this school actually go on to do great stuff. Another example that I wanted to sort of pull out is Henry Chapman's work on nanocrystals. And what you get in when you look at nanocrystals, so there are a lot of biological crystals that are difficult to make macroscopically large that could be used. You can determine their structure at sort of using traditional methods. And these nanocrystals are very fragile. They will melt in in a synchrotron beam much faster than you need, the amount of time that you need to solve for the full structure of that crystal. But it turns out in XFEL it's not a problem. You can still use basically a single shot or variation of single shots from multiple nanocrystals. In this case, you can see the Bragg peaks, but you can also see the fringes between the Bragg peaks. And essentially the fringes, you can think about these fringes as telling you the shape of the particle, and the location of the Bragg peaks telling you the structure, internal structure of the unit cell. And so in these experiments, Henry and his team were able to basically phase that and understand the structure of not quite a single molecule, but a very small crystal that would probably be very difficult or impossible to do using sort of traditional synchrotron scattering methods. And this is sort of another example. And the third example that I wanted to use, and this is the work by Jesse Clark, who is somewhere here at Stanford, where they looked at three-dimensional propagation of acoustic phonons inside of a single nanoparticle. And the idea is that basically they pumped it using the infrared laser, I believe, and created shock waves going through the lattice. And then the image, the expansion of the lattice in response to that optical excitations in nanocrystals by analyzing the diffraction patterns and inverting them. So that allows you to look at the shock wave or the phonon propagation inside of the crystal in 3D at this ultrafast timescales. And so the idea is that if you simply look at the location of the Bragg peak, you can see that it oscillates as soon as you hit it. So that's this the shock wave propagation, if you will, as a function of delay time between the optical pulse and the X-ray pulse that probes the system. But it can go one step further, and you can basically reconstruct not only the shape of the particle, but also the internal strain distribution, which tells you displacement field, so-called displacement field, which tells you what is happening inside of the nanoparticle as the phonons propagate and make the lattice expand and contract. And so this is the groups, a lot of science that I showed you. Some of this is work by several people, in particular Sebastian and Jim, and a little bit of Leandra. And so maybe I'll stop here, and I'm a little bit over my time, but I'll answer any questions that you guys have.
For more, please visit us at stanford.edu.